This lesson is about transistors in electronics. Here's a picture of a vacuum tube compared to two different transistors. And you can see why transistors, when they were invented, quickly started to replace vacuum tubes. Vacuum tubes are just much larger, they're made out of glass, they're fragile, they use a lot more power, they would get hot and burn out. Transistors were solid-state devices made out of all solid materials. You could drop them, they wouldn't break, and use a lot less power, just much better for many applications. And at this point in time, transistors have essentially replaced vacuum tubes in almost all of electronics. This is a close-up of two of the different types of bipolar junction transistors that this lesson is specifically going to be about. So let's begin learning about transistors by reviewing semiconductors and diodes. You can watch my YouTube video about semiconductors and diodes. Let's start by reviewing how a p-n junction diode works, and then we'll expand that idea into transistors. So here's a p-n junction diode. Again, remember the n-type material means it's silicon doped with some atoms that have extra electrons that are able to move through the crystal matrix. And p-type material is silicon doped with types of atoms that are missing electrons or have space for an extra electron that could be there. Essentially, they act as positive charges in a way. And then when you combine the p-type and the n-type material, electrons from the n-type will move into the holes of the p-type, and as the electrons move, that creates ions, so we have a depletion zone of positive and negative ions. And that depletion zone is important because what that does is prevent further charges from moving, whether it's electrons or the holes, considering them to be positives. If they try to move through that depletion zone, they get repelled by the other ions. And so once that depletion zone forms, it requires a higher voltage to push those extra charges through that depletion zone. So this is essentially how a diode works. But if you consider a transistor as similar to two diodes back to back, an n-type material and a p-type material, and then another n-type material. So we'll have two depletion zones, and we'll connect those n, p, and n material areas to three different wires. We'll call one the emitter, and then another one the base, and the collector. Then if we establish our polarity like this, with the collector being very positive, the base having a small positive charge, and the emitter being negative, think of electrons moving through this transistor. Electrons are negatively charged, so we can think of them as coming in the emitter region. Moving into the base, they'll fill up some of the holes, but more electrons can travel through that base region, so the electrons have to travel through that first depletion zone into the base area, then they'll travel through the second depletion zone and out through the collector, and some of them will travel out through the base. So if we put a positive voltage at the base and the collector, it'll attract the electrons in the middle P layer. Some current's going to flow from the emitter to the base, but most of the current will flow from the emitter to the collector. And it's the base voltage that will determine if the current flows and how much flows. If the base voltage is too low, there's really no current that's going to flow from the emitter to the base, or from the emitter to the collector. But the higher the base voltage, you'll get some base current and especially more collector current flowing. Bipolar transistors really are current amplifiers. Now we could think of it as conventional current flow from positive to negative. In that case, you can think of the positives as being holes. Put them in through the collector, they'll travel through the base and out the emitter. A few of them will travel down out the base, but most of them will flow to the emitter. Now whether we think of electricity as positive to negative conventional flow or negative to positive, the way electrons flow, really electricity is just the flow of charges, so we can think of it either way. When the inventors were designing the transistors, they were thinking of electrons flowing. But we get the same result whether we think of electrons moving or the holes moving. We can even reverse the type of materials. Instead of an NPN, we can have a PNP. And in that case, we could set up the polarity with the emitter being positive and the base and the collector being negative, the collector being more negative than the base. And if we think of conventional current flow being positives, we can imagine it as holes flowing in the emitter, through the base, and then a small current flowing out the base and the majority, the large current, flowing out the collector. Or we could think of it as electron flow, electrons coming in the collector and some from the base flowing out through the emitter. So bipolar transistors kind of act like two back-to-back diodes, but you can't just use two diodes and connect them together to have them work like a transistor, because you need those p-n junctions with the depletion zones. That's formed when the transistor is manufactured. If we think of it as two back-to-back diodes, the base emitter diode is forward biased, so current can flow from the base to the emitter. But the collector, the base to collector diode, would be reverse biased, so current cannot flow from the collector to the base. In a perfect world, that's how it would work. No component is perfect, so some leakage current will flow. If the base current flows, that causes the collector to emitter current to flow. So here's a picture of a 3906 or a 2N3906 transistor. It's a PNP type transistor, but there's no labeling on to indicate which lead is the emitter and which is the base, which is the collector. So either you have to just memorize that from working with these enough, or you can look up a data sheet. If you do a search on the internet for 3906 transistor, you can see a data sheet like this one from On Semiconductor, and it shows you physical look of the transistor. It's got the flat side, the curved side here, and a number 1, 2, 3 on the leads. Well, that corresponds to our schematic symbol, where 1 is the emitter, 2 is the base, and 3 is the collector. So it tells you the layout, and you can do that for any transistor. So here's how we would think of a transistor as two back-to-back diodes in a schematic. If you always connect a transistor to power. So here we have 12 volts that's going to supply the power. Current would like to flow through the collector and back out the emitter, or from the emitter to the collector. But it's the base that controls how much current that flows. So if there's no signal voltage on the base, the transistor will be turned off. There's no emitter to base current. So current can't flow from the collector to the base because that's a reverse biased condition. Think about, remember a diode schematic here. This triangle is the anode, that's the positive. The line indicates the negative. And so if we're using conventional flow, current would like to flow out here, but it can't flow backwards. And this diode, even though it's forward facing, forward biased, is not connected. So that represents an open. So there's going to be no current flowing. Since there's no signal voltage on the base, the transistor is turned off. There's no base to emitter current, no collector to emitter current. So any voltage difference between the supply and ground is going to be dropped essentially all on resistor 2. Since there's no voltage difference between the output and ground, there's no current that can drive any electronic equipment. But if we apply a small signal voltage to the base, and this is one thing that confuses a lot of beginners, the input does not need to be connected to the same power source as up here. It can be from a totally different power source. It can be, say, an input from an auxiliary output of an audio device, like a phone or a speaker. But if you put a small signal voltage applied to the base, the transistor turns on and there's a small base current that flows. That's going to allow a much larger collector current to flow. So the large current will also flow at the output. So no voltage on the base, the transistor is off. Voltage on the base turns the transistor on. Small base current results in a large collector current. You can replace an NPN transistor with a PNP transistor, and usually they'll work if you just reverse the polarity. And I also want to point out here that to remember NPN and PNP, this transistor is NPN, and the way I teach it to my students is the arrow in the transistor schematic symbol points the direction of current flow for conventional flow from positive to negative. And in this case, the arrow is not pointing in, NPN, not pointing in. But in this case, the arrow is proudly in pointing, so that's PNP. And that can help you keep straight NPN and PNP transistors when you just see the schematic symbol. But if you reverse the polarity, say make the emitter positive and the collector and base negative, then current will flow from the emitter to the base and the emitter to the collector. Now that's actually the direction that electrons are moving, but when we're using conventional flow, we would think of it as flowing backwards. So transistors are manufactured to be either switches or regulators typically. If they're switches, they need to turn on and off very fast. Switch transistors are usually used in applications for digital electronics, things like computer type systems, and they turn on and off very fast. But there does have to be some voltage bias to turn the transistor on. Or for a silicon transistor, that's about the 600 or 700 millivolts, 0.6, 0.7 volts. For a germanium transistor, it's lower, usually 300 millivolts, 0.3 volts. Regulator transistors instead are designed to usually handle more power, and they don't necessarily turn on and off as fast, but they are designed to amplify signals. So for example, if we hook up a transistor in a circuit with an AC voltage coming in on the base, that AC voltage is going to drive an AC current. So as current comes in, say that direction on the base, it's going to cause a base to emitter current to flow that same direction. But when the voltage reverses, that's going to cause the current to reverse direction, and that's going to result in a current flowing from the emitter to the base. So this diagram shows how the current would flow on the first half of the cycle of an AC wave, and then it would reverse and flow the opposite direction on the second half of the cycle. So if we put a small AC source coming in the base, we're going to get a larger AC current on the output. Same frequency, but a larger amplitude. So regulator transistors can act as amplifiers. And this is a schematic of how you would connect a bipolar junction transistor as a current amplifier in a circuit. We could use this first resistor RC as a current limiting resistor, so we don't send too much current through the transistor and blow it up and release the magic smoke. We could also use R1 and R2 in series with each other as a voltage divider circuit to control how much voltage we apply to the base. If we have a voltage on the base, that's going to drive the base current, which is going to allow a larger collector or emitter current. So our output signal is going to be much larger than our input signal. Here's an assignment I give my beginning electronics students to explore transistors. They just took this up on a breadboard. They use either a 9-volt power supply or a battery, and measure the voltage drops and the current moving through different areas of the transistor. This bottom question, the amplification ratio, that is essentially how much does the transistor amplify the current. So HFE or beta or amplification ratio, those are terms you'll hear, they're the same. And this formula shows that what it is the collector current divided by the base current. I represents current, C for collector, B for base. So we could measure the current from the collector to the emitter. That would be essentially the same as the output current. So we can measure that here. And then the base current from base to emitter. And if we divide the collector current by the base current, we get a number. For most bipolar junction transistors, that's somewhere between 20 to 200. And what that means is, say for example, if the beta is 20, if we had 1 milliamp of base to emitter current, we would have 20 milliamps of collector to emitter current. Or if the beta is 100, if we had 1 milliamp of base current, we would have 100 milliamps of collector current. So that's how much the transistor amplifies the current. Hopefully this has helped you learn a little bit more about transistors. I would encourage you to set up this circuit, explore it, try it out to learn more, and good luck. This is the breadboard layout and measurements of the transistor assignment. Here's the schematic. That's where you would put your leads to measure the voltage drop on resistor RC. Here's the next one, the 10K resistor voltage drop. Here's how you measure the 680 resistor voltage drop. Output voltage. Here is how to measure the base emitter voltage drop. It does look like right here that lead might be touching that resistor lead, but it's not. It's actually just touching the base. So you measure from the base to the emitter. Here's measuring from collector to emitter voltage. Collector to base, that negative lead is not touching the resistor lead. Here's how to measure the current. Remember, you have to open the circuit, so I've broken open the circuit by placing RC resistor's lead in an empty row, and then measuring current through the meter, back out of the meter through this lead and back to the transistor. The current from the 10K resistor. Output current, I stuck a yellow jumper wire in here as the output lead, measuring from it to ground. Current from just after the 680 resistor. This is a meter with a transistor tester, emitter, base, and collector, and then make sure the beta or HFE setting is selected. And this is a multifunction tester I have. It's not an expensive one, but you just have to put the correct leads in the correct slots and then push the start button. It makes a measurement, gives me my amplification ratio or beta of 214 and tells me what type of transistor it is, an NPN. There's lots of meters out there that will do this now. So that's how you make the measurements. Good luck and have fun.